Today we're going to be talking about electrons and atoms. This is the first of several videos where we discuss information about the electrons in the atom. So as you know, when you heat anything in a flame, certain light is often emitted, and that's different colors based on what is being heated. Um, Analysis of that light then can tell you what the chemical element is, and it can also tell you certain behavior about it. It tells us the arrangement of the electrons as well. And we have something called electromagnetic radiation. So that's a form of energy. It has a wave-like tendency. It also has a particle-like tendency that we'll talk about in a little bit. And visible light is part of that. There's other segments of that. So radio waves, for example, microwaves, when you heat your food. Infrared is heat. We have visible light, UV light. So that's the stuff that is an issue when you're out in the sun too much. X-rays, and then gamma rays. And gamma we studied in the previous chapter when we were talking about nuclear chemistry. And you can see here that as we move along this spectrum, that our wavelengths get shorter and our frequency increases. So down along the bottom, we talk about frequency. When we get to this section of the electromagnetic spectrum, that is the section that we need to be concerned about, because that is the section that can cause what they call this ionizing radiation. So it can change the structure of the elements and the electrons that are made up in that. And then that can cause funny kind of reactions to go on your body. You end up with cancer. And so there's the issues with that. So that's why we need to be careful with these. And as we move from ultraviolet to X-rays to gamma rays, you get even more energy being imparted because the frequency of that wave is coming across much faster. So we also have this section in here is called visible light, and we've kind of broken that out down here along the bottom to show you kind of how that plays out. So down here is your red section, and then up here is your violet. And you can kind of remember that because what's kind of next door to it. So here's your infrared. That's your heat, and then your visible light, and then ultraviolet. So violet is here, ultra would mean just a little bit more. So that's your light. In middle school, they might have had you memorize the Roy G. Biv, so the red, orange, yellow, green, blue, indigo, and violet is a common way that they have you memorize that breakdown of the visible spectrum. So all electromagnetic waves are going to travel at the same speed, which is 3 times 10 to the 8th meters per second. Now, this is in a vacuum. If we get light out of a vacuum and we're into some medium like air or water, that's going to slow down. But in here, we do all of our problems based on this being the speed of light. It just makes things easier. But this is why the speed of light slows down when you go into like water, for example. So things look distorted when you look through water. Things look shorter, the distances vary, and you get kind of a false impression of distance because the speed of light is slowed down in there. So we use this equation to solve some of our problems, where c is going to be the speed of light. This funny looking symbol here is called lambda, and that stands for your wavelength. And then this funny looking symbol is called nu, N-U, and that stands for frequency. So the speed of light, which is a constant, equals your lambda nu, your wavelength times your frequency. Your wavelength has to be in meters, and your frequency needs to be in 1/seconds or hertz. So again, frequency is the number of waves that pass a given point. It's expressed in 1/seconds. If you've gotten into math enough to know what an inverse is, it can be also inverse seconds, or it can be in hertz. Wavelength then is the shortest distance between two equivalent points on a wave, and it has to be in meters for us to be able to work with this. So here's a wave, for example. This is going to be our wave. Wavelength would be crest to crest, or you could have trough to trough. Amplitude is the height of the wave, and then the line here in the middle is called an origin. Inverse property, as our wavelength decreases, our frequency will increase, and as our wavelength increases, our frequency will decrease. All right. Sunlight is referred to as white light because it's going to contain all of those frequencies of light, but we can separate that into a spectrum using something called a prism. Raindrops can actually act as prisms, and that's where you get rainbows after a storm. Visible spectrum then of light only makes up a small part of the entire electromagnetic spectrum, and we saw that at the beginning. Here's that shot again showing you that we have a wide range in that. We also have something called a quantum of light or a photon of light, and when we solve problems for photons of light, we have to use something called Planck's constant. This is Planck's constant here. So it's 6.626 times 10 to the negative 34. That's going to be joules seconds, and we have to use that to solve our problem. The quantum or photon of light, the energy in that, is going to be equal to Planck's constant times the frequency. And again, frequency has to be in hertz or 1/seconds. And if you, we at some point, I believe, solve a problem and show you why the violet light has more energy than the red light, because it's more frequent. Photoelectrons then are emitted from this metal surface when we get certain light shining on it. And that's what allows our solar calculators to work. So we get light coming in, it's going to hit a metal in your calculator, and it's going to cause photons to pop off of here that have energy. And then that energy is going to be captured and uses electricity to fuel your calculator. So the energy of a photon has to have a minimum value in order to make that happen. So for example, if we had a minimum value of 2 electrovolts and we shined light in that had a 1.77 electrovolt, that would not be enough to cause that electron to pop off of there. But if you have that much or more, then it will cause it. And that's why sometimes with your solar calculators, they don't work in the dark or darker light. So here we have some problems that we're going to be solving. We need to have some equations that are handy. We have the speed of light equals the wavelength times frequency. Speed of light is a constant, and this stands for wavelength and this stands for frequency. So here we have a helium-neon laser. It's going to emit a wavelength of 633 nanometers. They want to know the frequency of that light. Well, the first thing that we need to do is we need to change these nanometers into meters. Let me see if I can get some different colors up here so I can represent this with some different colors. All right, so let's see if I can make this a little bigger. There we go. So the first thing that we're going to do is we're going to change our color of light over, and we're going to change that into, from our wavelength, we're going to change that into meters. So 633 nanometers. And if you think back to our nuclear, or not our nuclear, our metrics unit, we did dimensional analysis, and we need to figure out in 1 meter how many nanometers we have. And if we go back to our chart that I gave you at the beginning of the year, you'll see in 1 meter we have 1 times 10 to the 9 nanometers. So if we divide these two values, our nanometers will cancel, and that's going to leave us with meters. That will give us 6.33 times 10 to the minus 7 meters. And we can plug that into our equation where we have our wavelength, we have our speed of light, and we have our frequency. And then we need to get an equals in between here. There we go. Oops, that's not a good color, is it? Here, we'll do this one. There, that's better. All right, so we're going to fill in the information we know. We also need to isolate our frequency so we can solve for that. So if I do that, I'm going to have my frequency equals our speed of light divided by our wavelength. Okay, so that's going to equal our speed of light here. And I'm going to keep these in separate colors so you can see where my units are coming from. This is 3.00 times 10 to the 8th, and that's going to be meters per second. And then I'm going to put my wavelength in. I need to make sure that it's in meters. So I'm going to grab that, and that's going to be, I'm going to grab that and put that down here. So that's 6.33 times 10 to the minus 7, and that was meters. So now I'm going to solve for my frequency. My meters will cancel because anything divided by itself is 1. And that's going to leave me with a frequency here. I'm going to put this into my calculator. So 3 to the 8th divided by 6.33 to the negative 7, and I end up with 4.74, because I need 3 significant figures, times 10 to the 14th. And now we need to figure out what our units are. Well, I've got seconds on the bottom here, so I go 1 over seconds, or I could say hertz, because hertz equals 1 over seconds. And then we have that problem done. So the next problem, they're giving us a wavelength. They're asking us for a wavelength, and they're giving us a frequency here. So we need to solve for wavelength. So if I go back to my equation, C equals my wavelength times my frequency. If I want to get wavelength on the bottom, I'm going to have my speed of light equals, I'm sorry, let me back that up. Excuse me. I'm going to have my wavelength will equal my speed of light over the frequency. Okay, so now we're going to plug in our values that we know. And we have the speed of light, which is 3.00 times 10 to the 8th, and that's meters per second. Then I'm going to go in and I'm going to put my frequency in, which is 4.80 times 10 to the 17th. Now this is hertz, and remember, hertz is 1 over seconds. So wherever my value is here, that seconds is going to be on the opposite side. So seconds is going to go on the opposite line across from my frequency. And then if I go in and I cancel my units, my seconds will cancel out, and that's going to leave me with meters, which makes sense since we're studying wavelength. So when I put this into my calculator, I end up with 6.25, and it should be 3 sig figs, so we're good there, times 10 to the minus 10, and that's going to be meters. Okay, the next one, they're giving us a frequency in megahertz, and they want to know what the wavelength is. So again, we're going to solve for wavelength, use the same equation that we had before, and that's going to be speed of light over our frequency. But this time, our frequency is given in megahertz. And so we can't use that. We need to get that out of megahertz and get it into a unit that we can use. So 98.5, that's megahertz. If we go back to our metrics from the first unit, we put megahertz down here and we put hertz here. So if we look at mega, for every 1 mega we have a million hertz. No, yeah, million. There we go. So that's our calculation. So we need to put that in our calculator. So 988.5 times 1 million. And that ends up with a frequency of 985, and then I've got 1, 2, 3, 4, 5 zeros. And then I'm going to divide that into my speed of light, which is 3.0 times 10 to the 8th. And I did not put my units on here. I should have done that. That would have been hertz. So remember, hertz is going to go on the opposite side. My units for wavelength are meters per second. So I'm sorry, for speed of light is meters per second. So now I'm going to cancel my seconds here. That's going to leave me with meters, which makes sense because that's what I want my answer in is meters. It's a length. And so I'm going to take my values here, divide them out, and I end up with 3.06. Yep, 36 figs, and that's going to be meters. And that should be your answer to this problem. And then the next one that we're going to be doing is energy. And so we'll pick that up on the next video.